Hello, you are welcome for the Applied Electricity tutorial session. So kindly get ready as we begin soon with the tutorials. Okay, so I guess everyone is set for this tutorial, and let's get straight to what we have for you in this tutorial. So with Applied Electricity, I'm going to start from series and parallel connection of resistors, how to find the effective resistance of series and parallel connection of resistors. So let's say you have resistors, that's what we are talking about. So resistors, they are permanent. The, resistors are elements in a circuit which opposes the flow of electric currents in the circuit. So resistors are represented like this, connected to the connecting wire in the circuit. So the interest now is, if you have more than one resistor, that is two or more resistors, and they are connected in series and parallel, how do you determine that these two resistors are connected in series or parallel? So let's start with series connection of resistors. So series connection of resistors. So now, when we say two resistors are in series, first of all, we have some conditions two resistors must satisfy for us to say they are in series. Now let's see. First of all, for two resistors connected in the circuit to be in series, then there should be no node between the resistors. So there shouldn't be any node between the two resistors. And if there is no node between them, then obviously the same current is going to flow through the two resistors. Now, when you say a node, this is the keyword here. What is a node? So if you have a circuit with resistors and a power source like this, as I have drawn here, you realize that the voltage source here is going to produce a current through this wire. At this point, the current coming in would have to make a decision of either to pass here or to pass here, or if not, part of it is going to pass here and the rest will pass here. At this point, we call this a node. So a node is a point in an electrical circuit where a current make a decision, or where current split or combine. So now, as I said, the condition for series connection is there shouldn't be any node between the two connected resistors before we say that the two resistors are in series. So now let's see. We can have a circuit like this, and you'll be asked that this is, let's say, resistor 1, resistor 2, resistor 3, then resistor 4. So now, seeing the condition here that for two resistors to be in series, there should be no node between them, you ask yourself, is this a node? No, this is not a node. Likewise, this is also not a node. The reason why I'm using this illustration is sometimes people get confused about what a node is. A node is not simply mere a corner. Yes, it's not a corner. No, every node, you should make sure that when current is arriving at the node, it will have more than one chances or more than one path. So assuming current is flowing through this path as I1, upon reaching here, the current has no other option except to move to this. So this is just a straight wire. But for the purpose of clarity, if you are drawing a circuit, we just need to, curve it so that it becomes like this for easier representation. So this is not a node. For that reason, resistor 1 and resistor 2 will have the same current passing through it, and hence they will be in series. Now let's consider resistor 3 and resistor 4. These two resistors here, we can clearly see that when current is flowing, there wouldn't be any node here. Though this is a power source, yes, current will flow, that is the positive will flow this side and the negative will flow this side. So the current flowing through it is of equal magnitude. Hence, R3 and R4 are in series. Likewise, R1 and R2 are in series. So this is a slide representation of series connection of circuits. Now, let's go to parallel connection of electrical circuits. Okay, so for the parallel connection of circuits, let's see the conditions applied to that. So parallel connections. For parallel connections of circuits, the condition to be satisfied is that 1, there should be a node. So there should be a node between the two resistors. So the first condition, there should be a node between the two resistors, right? So that is the first thing you observe when you are giving any two resistors, for you to consider them and also check if they are in parallel. Then there is one condition 2 here, and the condition says when you traverse through them, when you traverse through their paths, you shouldn't meet, when you traverse through their paths, you shouldn't meet any other element, any other circuit element. So the first condition is there should be a node. There should be a node, that is presence of a node between the two resistors. And the second point is when you traverse through their paths, you shouldn't meet any other circuit element. So let's see how you apply this to determine if two resistors are in parallel. I have a circuit for this illustration. So I have this circuit here. Then so let's see this circuit. Let me label the resistors so you understand it well. So let's say this is resistor 1, resistor 2, resistor 3, resistor 4, resistor 5. We are to determine which of these resistors are in parallel. So to begin, always ask yourself the first condition. What are the two resistors you are considering? Now let's consider R1 and R2. So for R1 and R2, you realize that there is a node in their path. Hence, the first condition is satisfied. Then the second condition, which said when you traverse through their paths, you shouldn't meet any other circuit element. How do we apply that? So kindly watch as I do the illustration. So R1 and R2. So when you traverse, it means that you're going to move along their paths in a loop-wise manner. So you move through it this way, and you realize that they are the only circuit element which you are going to meet. You shouldn't meet any other circuit element. Hence, R1 and R2 are parallel to each other. So, sorry. So they are parallel. Now let's see R2 and R4. These two resistors, you can clearly see that between these two resistors, there is a node here as well as there is a node here. Hence, the first condition is satisfied. Now, when you traverse through them, let's see. If I move through these two resistors, across these two resistors, you realize that I am meeting a third resistor here, which is resistor R3. Hence, my condition is not satisfied. Hence, R2 and R4, they are not parallel. So always make sure you ask yourself these two conditions, and they will be in parallel provided the two conditions are satisfied, not even one. That is why in this case, you realize there was two nodes which satisfy the presence of a node between them, but when we traverse through their paths, we didn't meet any other circuit element, right? Now let's see R4 and R5. R4 and R5, is there any node? Yes, this is a node, because when current is coming in, it will either pass here or pass here. That is, a decision is going to be made. Now, this point to there is a node. Likewise, when current is coming in, it will either go up or come here. Hence, the first condition is satisfied. Let's see, when you traverse through their paths, you shouldn't meet any other circuit element. So I'll move through their paths in a loopwise manner, and you realize they are the only two elements in this loop. So therefore, resistor R4 and resistor R5, they are parallel to each other. So I hope with this illustration, you will be able to remember the conditions for parallel and series connections of resistors in a circuit. Now let's move straight to how to find the effective resistance of a circuit. So we have to find the effective resistance of complex circuits. So before we find the effective resistance, let's see how to find the effective resistance of simple circuits, that is considering two resistors. So if I have two resistors, that is R1, R2, and they are in series, how do I find the effective resistance? So if R1 is in series with R2, the resistance, that is the total resistance across these two resistors. So the illustration is this. I have my R1 here, which goes into my R2 here, and the two will move to a source down here. So you can see that these two resistors are in series because there is no node between them. How do I find the effective resistance of this? This is a simple circuit. I'm illustrating the effective resistance to you. So you realize that the effective resistance RT, which is also called the total resistance, is equal to the sum of the two resistors R1 plus R2. Now the reason behind this is the same current is flowing through. So you just add the magnitude of the resistors, that is their resistances, then you get the effective resistance. Now, what about two resistors which are in parallel? So in parallel connection, you have resistor 1 up, probably you have another resistor down here. There is a branch here, and this branch will also go into our source here. So this is R1, this is R2, and this is our source voltage. Since these two resistors are in parallel, because there is a node here, there's another node here, hence the node is satisfied, presence of a node. And if I traverse through the path of these two resistors, I'm not meeting any other elements, hence R1 and R2 are parallel. But to find the total resistance or effective resistance of these two resistors is given by 1 over the total resistance will be equal to 1 over R1 plus 1 over R2. And from this section, it can further be simplified as 1 over RT is equal to R2, that is, you multiply, plus R1 all over their product, R1, R2. We need a total resistance, not 1 over RT. For that reason, our RT is simply the inverse, that is R1, R2 all over R1 plus R2, right? So this formula and this formula are the ones we are going to use to solve the effective resistance of complex circuits that we'll be solving as part of this tutorial. Now let's get into solving our problems. So we'll be finding the effective resistance of some circuits. Then we'll apply the parallel and the series connections. So let's see the first problem I have here. So problem 1. So let me make it question 1. So for question 1, let me give a simple circuit here. So I have this resistor to be 4 ohm, and I have this to be 2 ohms. Then I have this to be 2 ohm as well. Then this to be 2 ohm, then 1 ohm. And I have a 10 volt source here. Now we are to find the effective resistance of this circuit. So there's the question. We have to find the effective resistance of this simple circuit here. To begin with, the first step is take two resistors at a time. Take two resistors at a time. Please, these are the tips on how to go by finding effective resistance of complex circuits, no matter how big the circuit is or no matter how complicated the circuit is. The first key is to take only two resistors at a time. The second part is work away from the source. Work away from the source. Work away from the source. So when you start, you work away from the source, then gradually you move towards the source. The reason is, when you have this circuit and you want to find the effective resistance, we don't start from where the source is, that is this resistor. No, always try and start away. So we are going to start from branches away from the source, then gradually we will converge into the source. From our example, we have these 2 ohm here, 4 ohm here, which is on a branch away from the source. Likewise, we have this branch here carrying 2 ohm resistor and another 2 ohm resistor. these two branches are away from the source, and you can start from any of them. So taking the solution of this simple circuit, you realize that these two resistors, are they in series or parallel? That's the question you're going to ask yourself. So you ask yourself, is there a node? So one, presence of a node. You ask yourself, is there a node? So 2 ohm resistor, 4 ohm resistor. This is the branch. And between them, you only have this junction here. So is this a node? No, this is not a node. So the answer is no. Once your answer is no, it can never be parallel, because for parallel connection, it should have a node. So once it is no, then it means it is a series. So meaning 2 ohm resistor and 4 ohm resistor are in series, and hence that place will give us, so let me make it this way. Our 4 ohm resistor is in series, so plus 2 ohm resistor, right? And that will give us 6 ohm resistor. And at this point, I'm going to clean the branch and replace my effective resistance with just a single resistor, and that is going to be 6 ohms, right? I come to this side, 2 ohm, 2 ohm. Are they in series or parallel? Hence, I ask, is there a node? So this place, there is no node here, hence they can't be parallel, and they are in series. For that reason, I'm going to get 2 ohm resistor plus 2 ohm resistor. That's going to give us 4 ohm. And I'll clean this branch also, and I'll replace it with a single resistor of magnitude 4 ohm. So you can see that we have simplified the circuit, and we have one resistor here, then you have a resistor right at the source. With this arrangement, we still consider resistors away from the source, and remember, we take 2 resistors at a time. So I have 6 ohm resistor here, I have 4 ohm resistor here. They are the 2 resistors away from the source, and it will be considered first. So I have 6 ohm, then 4 ohm. Are they parallel or series? When we see this node between the 2 resistors, they cannot be series. Then they are parallel. But you can't confirm just the mere presence of a node. I told you the second condition is to traverse through their paths. If you don't meet any other elements, then they are in parallel. So when I move this way in their path, I'm not meeting any other elements. For that reason, 6 ohm is parallel to 4 ohm. And I'm going to get from my RT in the parallel resistance, realize it's R1 multiplying R2 all over R1 plus R2. And this is giving us 6 times 4 over 6 plus 4. That's going to give us 24 on 10, which is equal to 2.4 ohms. Hence, I will clean these 2 branches and replace it with a single branch. So I'll clean this, then let me maintain the other side. So I'll clean it, and at this point, I'll have a simple circuit, but this time around, the 4 will go away, and the 4 will be replaced with 2.4 ohms. So this 4 will be replaced by what? 2.4 ohms. And at this point, my circuit is now simplified. So you can see that I'm close to the source, and the only 2 resistors are 1 ohm and 4 ohm resistor. Are they in series or parallel? Is there a node? You can see there is no node here. When the current flows, it flows freely and come back to the source. Hence, 1 ohm is in series with 2.4 ohm. So my RT finally becomes 1 plus 2.4, which will give me 3.4 ohms. This is how we solve a simple circuit. We found the effective resistance of a simple circuit. Now, before we proceed to finding the effective resistances of complex circuits, we have to do short circuits and open circuits, since complex circuits have these branches in them. So in order for you to understand when we are simplifying such circuits, we need to go through short circuits as well as open circuits. Now, What is a short circuit? You may have heard short circuit severally, but now in applied electricity, we learn short circuits and how it affects a circuit. So a short circuit, theoretically, that is conceptually, it is a branch. So let me make it. So a branch of zero resistance. That is, if you have a branch in a circuit and the branch carries zero resistance, that branch is said to be a short circuit. So this is a theoretical concept. And a branch is a piece of wire connecting two nodes. So if I have a bigger circuit like this, and I have one part like this way, then I have my source here. Now, please watch carefully. This is our voltage source. This is my first resistor, and this is my second resistor. I'm talking about short circuit, a branch of zero resistance. What it means is that this branch, current will pass through that particular branch without any resistance. And apparently, they are the branch which are not carrying any resistors on them. So let's see this circuit. You know that the longer part of our voltage source is the positive and the short part is the negative. Positive will flow up, and upon reaching this first node, it will ask itself, where am I passing? And please take note, when current is flowing, consider the current as water flowing through a pipe. When water is flowing through a pipe, it doesn't take the path with what obstacles. So assuming I have this, I'm making this illustration to you. I have a tap up here and it's connected to two branches. That is, it has been divided into two parts. For this part, I have a big stone here, and this part is just, so let me make it well. So this part is just an open tunnel moving out. If water is being poured into this, you realize that the water, upon filling, it will just stop here. Some will escape and pass through here, but majority of them will flow freely here. What it implies is when a current reaches a node, it is going to sense these obstacles in its path, and it will sense these free paths. And you being the shoes of the current, you realize that you've just passed here because it's easier for you to pass through a path without any resistance than you to struggle through, obstacles in your path. For that reason, the current coming from the voltage source will simply move straight through this path and return to the circuit without passing through any of these resistors because it has already sensed a free path. This is the concept of short circuits. So let's see how we will apply it in simplifying complex circuits. That is finding effective resistance of a complex circuit. Now let's see how to identify resistors which have been short-circuited. As we proceed, we will be applying this concept very well. So please take attention in this section. So I'm going to draw a circuit for us to identify the resistors which have been short-circuited. So let's see, I have this circuit here, my voltage source going into one resistor, have this branch here, so this side. So let's see, then this way. So these are voltage source are R1, R2, R3, R4. Now we have to identify the short circuit and also the resistors which have been short circuited. This is a complex circuit having 1, 2, 3, 4 resistors. But you ask yourself, Are all these resistors active? No. So let's follow the path of the current. V is going to produce a current I. I have no option except to pass through this R1. That is the R1, the resistor here. So it will manage to pass through this obstacle. Upon reaching here, it can't continue journeying further while there is a free path here, because you can't just, you want to get back home early and there are these obstacles here. You just take the shortcut. So short circuit is simply like a shortcut, you get it? Shortcut to your destination. And as you are leaving home, you're surely coming back home. So you have to skip all these three resistors, then return back this way. So I will come, then finally I will return back to the voltage source. Hence, effectively, this circuit is this way. So this is the effective part of this circuit. Only R1 is working. R2, R3, R4 have all been short circuited. And this is the concept of open circuit. It's so clear from the name, open circuit. That is a circuit which has been not open, right? So let's see. An open circuit, it's a branch with infinite resistance. So if you have a circuit and the circuit has a branch with infinite, remember short circuit is 0. So the opposite of short circuit is open circuit. So you have a branch, but that branch has an infinite resistance. So we call that open circuit. And infinite resistance means that the current coming cannot overcome such obstacle because it's infinite. So let's see. I have load, let's say a source here going into R1, R2. Then it's moved this way. This place there is an open branch here. Then to this side. So R1, R2, R3, R4, R5, right? This is a voltage source. Current is going to flow through this way. Upon reaching here, the current is going to sense that in this branch, you can clearly see that this side and this side are discontinuous. Current cannot jump through the air. You get it? So that is what we call infinite resistance. There is no way the current can jump from this to this. For that reason, once the current is flowing upon reaching here, we'll sense that if I go, and take note, if a current pass through a resistor here, a branch here, it is going to return through this side. So if no current is flowing through here, then no current will return through this part because it's a cycle. It goes and it comes back. So when it reaches here, it's going to sense that this side, I can't move. There is no way I can go because the obstacle there, it's infinite. For that reason, it won't even go for part of it to come back here. So once it reaches here, it will come down and enter the resistor back again. The circuit, the voltage source. So this is the effective circuit here. Our V, then R1 like this. So this circuit is the same as this because our R2, our R3, our R5 and R4, they are all not active. And this is the concept of open circuit. So hope you've understood short circuit and open circuit. So as we proceed, we are going to apply this to find the effective resistance of some circuits. So let's take our second example, that is question 2. In this example, we are going to apply all the concepts learned so far. So I have a 4 ohm resistor here. I have this branch. I have this. Then I have this. So there's 4 ohm, 3 ohm, 7 volts, 2 ohm. So the question is, determine the total resistance of this circuit. Determine the total resistance of the circuit below. So let's see how we're going to solve this problem. We have the voltage source here, 7 volts. 4 ohm, 3 ohm, and 2 ohm resistors. Always, if you are given a circuit for you to simplify, just follow the path of the current. Where is the current starting from? It's going to start from this 7 volt. So you just indicate some kind of I here. So you realize that this current upon reaching here was split. But now, to find the effective resistance, we are only interested. Okay, so now let's see. I'm going to use the arrow. So in this problem, we have 4 ohm here. That is 4 ohm here. Then we have 3 ohm here. We have 2 ohm here. We are to find the effective resistance of this circuit here. You ask yourself, from the conditions I stated, we take 2 resistors at a time. So 2 resistors at a time. For that reason, we are going to consider 2 resistors alone. Now, the second part is you are to simplify resistors away from the source. Then we gradually come to the source, right? So now let's see. I'm having this 4 ohm here and this 2 ohm here away from the source. This 3 ohm here is directly at the source and we can't consider it at the first. So we only consider 4 ohm here and the 2 ohm resistor here. So for that reason, you ask yourself, 4 ohm and 2 ohm, are they in series or parallel? Now, before we go to that, we can clearly see that there is a branch here without a resistor and it is also away from the source. So let's trace the path of the current. So I think for you to begin a circuit which has a source, so far as your circuit is having a source here, if you are to find the effective resistance, then what you are going to do is you are to create the current from its source and trace its path for us to know the effective circuit of this entire circuit. So now let's consider the effective circuit. You realize that this current I here is going to flow, and upon reaching here, we'll have to make a decision because part of it can pass here, it can also, move forward, but it will sense this free part. Please take note, there is a free part here. It is going to sense this free part as well as sense this part here, which has a resistance of 4 ohm, and also this part which has a resistance of what, 2 ohm. And I told you that current seeks to find a path of what, free obstacles. The current doesn't like paths with resistors, and resistors are obstacles. So it will simply move here, I, then it will come and pass here, I, also return back I, then come back to the hot circuit I. So you realize that it is only this part of the circuit working, and the entire circuit, the effective part of the circuit is this part. So it is the 3 ohm here and the 7 volts, which is the effective part of this circuit. You realize that the 4 ohm and the 2 ohm have been short circuited, right? So at this point, we can clearly see that the only resistor here is 3 ohm. So our RT is simply equal to 3 ohm for the entire circuit. We are done with this problem. Let's consider another problem and see how we find the effective resistance. So our problem 3. So let's quickly move through this problem and see. I have this here. I have this here. Then I have this. So I'm to find the equivalent resistance of this circuit. Equivalent resistance of the circuit. I have my voltage source V here, 1 ohm, 2 ohms, I have 3 ohms, and I have 4 ohms, 5 ohms. I'm to find the effective resistance of this circuit. you just take your time, and if you have a voltage source, I told you you have to get the effective circuit before we can proceed. So this voltage source here is going to produce a current I here. Then a current I will pass through this side, through this 1 ohm resistor, because it has no other option. It's only one way. Upon reaching here, there are multiple paths, either pass here or they will pass here, right? So at this point, when it is passing through this side, it will also arrive at this junction. Part of it will pass through here, then part will also pass through this side. So upon reaching here, it will then make a decision. There is one part here, there is another part here, but this part is free. There is no resistor here, but there are obstacles here. So to rather take this part and also return back in this manner. For that reason, our effective circuit, which is the V, goes this way, comes this way, like this, like this. So here is our 3 ohm, our 2 ohm, then our 1 ohm. So at this point, finding the equivalent resistance becomes simpler. I told you take 2 resistors at a time and you work away from the source. So I'll take these 2 ohm here and these 3 ohm since they are away from the source here. So you realize that 2 ohm and 3 ohm, what's the relationship? Are they in series or parallel? There is a note here for that they can't be in series. And what else would it be? You realize that when you traverse through them, they are the only 2 resistors, hence they are parallel. For the parallel connection of 2 ohm and 3 ohm, the effective resistance RC there will be 3 times 2 over 3 plus 2, and that is going to give us 6 over 5, 1.2, right? So you already draw the circuit, and at this point you have our 1 ohm, but this whole part will be replaced with the effective resistance, which is what, 1.2 ohm, and this is the voltage. So therefore our total resistance at this point, you have only 1 ohm and 1.2 ohm resistors away from the source, hence there is no node and the same current will flow through them, so they are in series, and our total resistance or the equivalent resistance becomes 1 plus 1.2, and that is giving us 2.2 ohm. And this is simply how to simplify such circuits. Now let's go to our next example, question 4. So for this example, I'm going to have this circuit here. So I have this, then this will go into, so I have this resistor here, this here, this here, so this, like this. So this place is 6 ohm, this place is 3 ohm, this place is 4 ohm, here is 4, this place is 3.3 ohms, and this place is 1 ohm. And the question is, calculate the effective resistance you see the shape, really. Okay, so let's continue. The problem is calculate the effective resistance of this circuit, and I have these 2 terminals. Across the 2 terminals, I have a set of resistors here, 1 ohm here, 3 ohm here, 6 ohm here, 4 ohm, 4 ohm. And I am to find the total resistance of all these resistors. And the rule, as I said, is that you work away from the source and we take two resistors at a time. So in this section, you realize that this resistor here is 6 ohm, then this resistor here 4 ohm. So you realize that this 6 ohm and this 4 ohm are away from the terminal. So we work away from either the source or the terminals, right? Because these two terminals will be connected to a voltage source. So it's advisable to work away. And working away, this is the farthest part. And the two resistors we can consider is 4 ohm and 6 ohm resistors. So the question is, are these two resistors in parallel or in series? Because they are the two we are considering first. When I consider this part, there is a node here. There is another node here. Please, this is not a node. Once there is a node, then it means it can't be series. So series is not an option, but rather it can be parallel, but not entirely, unless it satisfies the second condition that when I traverse through the path, I shouldn't meet any other element. For that reason, when I move along the loop like this, you can see that I'm only seeing 4 ohm and 6 ohm. For that reason, my 4 ohm is parallel towards 6 ohm. So you do it step by step, right? And as you do, you clean and you redraw your circuit. Now, 4 ohm, 6 ohm, they are parallel. This is a symbol. And what will be the total resistance or the combined resistance of 4 ohm and 6 ohm? I'm going to have 6 times 4 over 6 plus 4. This is giving me 24 over 10, same as 2.4 ohms. And once I simplify it, I will remove the two resistors and replace it with only one resistor of magnitude 2.4 ohms. So watch closely as I clean. So you can see that this side, the 4 ohm and the 6 ohm now should be replaced by a single branch, right? So replace the 4 ohm and the 6 ohm with a single branch with a single resistor, which is 2.4 ohms. That is our first simplification. And at this point, you can clearly see that we are left with 3 ohm and 2.4 ohm being the resistors at the farthest end. And we will continually combine till we move to the terminals. So now this 3 ohm and the 2.4 ohm, are they in series or parallel? This is the joint between them, and you can see there is no node here. That node has been removed. So 3 ohm is clearly in series with 2.4 ohm because the same current will pass through them. Hence, 3 ohm plus 2.4 ohm will give us 5.4 ohm. I've now combined these two resistors, so gradually we are moving, meaning I have to clean one of them and replace it. I have to clean the two and replace it with a single resistor that is the effective of value 5.4 ohms here. So let me take this off and I'll clean this side. I'll close the branch this way. So now this 3 ohm here has already been combined with the 2.4, and the effective resistance here will be 5.4 ohms. That is from this side. So the first part and the second simplification. Now we've read this portion. At this portion, you can clearly see that we have 5.4 ohms and 4 ohms away from the source, and we are taking these two at a time. When I move through these two resistors, there is no other resistor or any other element, hence, and the presence of this node makes these two in parallel. So therefore, 5.4 ohm is parallel to 4 ohms. And your parallel connection will give us 5.4 times 4 all over 5.4 plus 4. And what would that be? So we solve this on a calculator. 5.4 times 4 over 5.4 plus 4. Please punch it into the calculator as you watch closely to confirm answers also. So I'm getting, please, there is one thing you're supposed to know. Whenever you are doing applied electricity and you are simplifying, never leave your answer in decimals until you are done simplifying all the resistors. So assuming we combine here and we get a fraction, please use the fraction as you proceed until the last part. So that is just a caution. So at this point, we are going to get 108 over 47 ohms. And this is the combined effect of 4 ohm and 5.4 ohm. And I have to replace these two resistors with a single resistor of magnitude 108 over 47 ohms. So I'm to clean the branch once again. This whole branch is going right now. I'm left with this. So the 4 ohm will also go, and I'll replace it with 108 over 47 ohms. Right. At this point, my circuit has become very simple. And what am I considering? I have 1 ohm and 108 over 47 ohms farther away from the terminals here. So these two resistors here, are they in series or parallel? There is no node between them, and you can see that the same current will flow through. For that reason, our 1 ohm is in series with 108 over 47. So we simply add their magnitude to get their effective resistance over 47. So 108 on 47 plus 1. That will be giving us 155 on 47. Hence, I'm going to clean these two and replace it with a single resistor of magnitude 155 out of 47, right? So I'll clean this. So I have this branch here, and this part is 155 on 47. So now at this point, what do you see? Our circuit has now been simplified to only two resistors available here. How do we simplify these two resistors? Once again, we need to see that they are either in series or parallel. So how do we notice that? Is there a node? Yes, because please take note, the terminal A here has a node here, and there is a terminal B here. So A will split. Let me clean this portion so you see it well. So there is a node here, and don't think that it is just a single point, so the same current. No, there is a node actually here. So let's redraw this well for you to see the node. So redrawing, you draw one of your terminal here as A, and you draw as B here. And at this point, this branch here, we will straighten it up so that it becomes straight. So it will move out, and we will draw this straight branch here, and that will be 3.3 ohms. This part will also continue as another branch like this, and that part will be what? 155 over 47 ohm. I think with this expansion, you can clearly see that our 155 over 47 is in parallel with 3.3. All over 3.3 plus 155 over 47. So let's see. 3.3 times 155 over 47 over 3.3 plus 155 over 47. and that is giving us 1 point. So let me clean this part so you see the answer. Let me write it somewhere here. So you realize that our total resistance RT from this expression here is giving us 1.649 ohms, and this is the effective resistance of the circuit we started with. Please, this is the end of this particular problem. Now let's move forward, but before we proceed, we need to consider the third resistance connection, and that is what we call the delta star transformation. So once you get a delta star transformation, it will also help us to simplify a more complicated circuit. So let's see, delta star transformation. So in this section, one may ask, is it possible for two resistors not to be in series nor in parallel? So neither in series nor parallel. Yes, the answer is yes. Two resistors may not be in series, neither in parallel. So how do we treat that, or how do we go about that one? So now, for delta star transformation, it involves, as you know, whenever we are simplifying circuits, we take two resistors at a time. Now let's see. We know that for parallel connection, it involves presence of a node. Then the second condition was, if you traverse through them, you shouldn't meet any other elements. So in a case where when you traverse through them, you meet a resistor, that is where the delta star transformation sets in. So how do we go about that? Now let's see. Let's start with delta. So delta, I have this arrangement of resistors here, like this: R1, R2, then R3. I have this point here, I have this point here, and I have this joining a circuit. And upon seeing this, you realize that these three resistors here, as you're having, if you want to simplify them, the rule says you have to take only two at a time. So let's say we are taking R1 and R2. Are they in series or parallel? So there is a node here, meaning they are not in series, but that doesn't mean they are in parallel. And you are going to traverse through them. You shouldn't meet any other element aside R1 and R2. But in this case, if I traverse through them, I'll pass here, then I'll meet R3 here. Hence, they are not in parallel. So not in parallel, they are not in series as well. When I take R2 and R3, there's a node here, they are not in series, yes. But when I traverse through them, I'm meeting R1, hence they are also not in parallel. Likewise, R1 and R3. There's a node here, meaning they are not in series. Then when I traverse through them, I meet R2 here, meaning they are also not in parallel. Meaning that these three resistors, we can't simplify them using the parallel and series connection, but we introduce a new concept which we call the delta star transformation. So if you have any three resistors arranged in this manner, we call it a delta. Please take note. It may not be triangular. It may also be in a rectangular form this way. You have one here, then you finally have one down here. You get it? So at this point, this R1, R2, R3 is said to be in a delta form or delta arrangement. So either this or this is what we call the delta arrangement of resistors. Now let's see the star arrangement. So star arrangement of resistors. Considering the star arrangement of resistors, we are going to have resistor arrangements like this, then like this. So I have R1, R2, then R3. So with this resistors arrangement, there is no way, there is a node here. For that reason, none of them can be in series. So it can't be in series. And you can't say any of them is in parallel. I mean, any two of them are in parallel. No, because it's just an open circuit here. So this is what we call the star arrangement. So now you've seen delta star, but our interest is to know how you convert it from delta to star or star to delta, so that we can solve it or simplify our circuit. And that is what we are going to do in our next part. So let's see star to delta transformation. So star to delta, meaning I need to draw my star, then I convert it to delta. So this is star arrangement. Let me make it bigger. I have R1, R2, then R3. The delta arrangement, if I want to convert the star to delta, what you do is any two of the resistors, you close their end with another resistor. So you close this part with a resistor A, you close this also part with another resistor B, then finally we close this end with another resistor C. You can see that we have the delta outside and the star inside. Upon finding the values of A, B, and C, I can clean my star within and I'll get my delta outside. So how do I find A, B, and C? A is equal to, please pay attention in this part and let's see how the arrangement is going to be. So to find the resistor A, the rule is this resistor A here is enclosing these two resistors R1 and R2. So what we do is we sum them. So you are going to get R1 plus R2, right? Because it is enclosing. I just want to show you how you can always memorize the formula. So this resistor A here is enclosing R1 and R2. So you just sum them, R1 plus R2 plus the product of the same two resistors, R1, R2, over the opposite resistor here, R3. Let me take it again. To find A, which is enclosing R1 and R2, you only sum this R1 and R2 and also add it to their product, R1 and R2, over the opposite resistor, R3, which is this part. Likewise, B, enclosing R1 and R3, so R1 plus R3 plus their product, R1, R3, all over the opposite, which is what? R2. Then finally, I have C, enclosing R2, R3, so R2 here plus R3 here, plus their products, R2, R3, all over the opposite, which is what? R1, and that is this side. So this is how we convert from star here to delta. Now let's see the other way around. The other way around is going to be delta to star. And for this, I'm going to draw my delta here like this. So I have my R1, R2, then R3. Then to find the star transformation, you draw a resistor between each of the two resistors here. So within this, I'll draw one here, a node here. I'll draw another one between here, then finally another one here. A, B, C. Upon finding the values of A, B, C, my delta will then be transformed into what? A star. What are the values of A, B, C respectively? A is equal to, now let's see, A finds itself between resistor 1 and resistor 2. So what we do is we multiply them. R1, then what? R2 over the sum of all the other three. R1 plus R2 plus R3. So that is that. The resistor which is, the two resistors which A is between, you multiply them over the sum of all the three resistors. Hence, B is simply equal to R1, R3 over the sum of R1 plus R2 plus R3. Then C is between R2 and R3, so we're going to have R2, R3 over R1 plus R2 plus R3. And this is what we call delta to star transformation. Now let's take some problems and see how this is practically used. So the question on delta star, 30 minutes more. Okay, so let's see. So I'm giving a question here for us to find the effective resistance in a delta star transformation. So let's see how you're going to do that. So I have this. Let me clean it back and draw. So I have this here. Then I have another one here. I have one here. There is a terminal here A, terminal here B. So this is 6 ohm resistor. This is 6 ohm resistor, 3 ohm resistor, 3 ohm resistor, 6, 3 ohm resistor. The question is, determine the total resistance seen between terminals A and B. Okay, so let's go on. I have the two terminals A and B this side. So 6 ohm, 6 ohm, 6 ohm, 3 ohm, 3 ohm, 3 ohm. What is the rule? The rule is that you are going to start away from the source. This is the terminals. So we have to start away from the terminals. And remember, we are taking two resistors at a time. Now, away from the terminals, I can start above here or this side. If I take 3 ohm here and this 3 ohm here, now let's see something. There is a node here, there is a node here. Yes, they can't be in series. But if I traverse through them, I'm meeting this 6 ohm resistor here. Hence, they are also not in parallel. And that should come in mind that we have a delta arrangement here. When I come up here too, you realize that this is ohm and this is ohm. There is a node here. But when I traverse through their path, I'll meet this third resistor 6 ohm. Here is also in a delta arrangement. And if you open your eyes, you can see clearly we have a star arrangement in the middle here. Now, how do we begin? We learned about delta to star transformation, and this problem is where we're going to apply it. So please watch closely as I illustrate the delta to star transformation properly here. So this is a delta. We have to convert this to star before we can solve this problem. How do we do that? Now let me redraw that circuit and put in the star form. So you see, so this is it, then this is it, A, then B. So this is our 6 ohm, 6 ohm, 6 ohm, 3 ohm, and 3 ohm, 3 ohm. So I'm going to draw my star inside here this way. And I told you we put each resistor within any two. And within this and this, I'll put my third resistor here. And I'll label A, B, C, right? So this is the first conversion of this system into what? Delta. Let's find the values of A, B, C. To find the values of A here, I told you that from delta to star, what do we do? Let's go back. I told you that you multiply the two resistors which A is between them over the sum of each of the three other resistors. Now, A finds itself between 6 ohm and 6 ohm. I'll multiply them 6 by 6 over the sum of the three. 1, 2, 3, that is 6 each. 6 plus 6 plus 6, and that is giving me 36 over 6, 6, 6, that is 18. 36 on 18 is 2 ohm. My B, which is also between 6 and 6, is similarly 6 by 6 over 6 plus 6 plus 6, giving me 36 over 18, which is equal to 2 ohms. Finally, C equals 6 by 6 over 6 plus 6 plus 6, giving me 36 over 18, also 2 ohm. Now we've transformed our A, B, C, and let's replace them with the respective values. A is going to be 2 ohm here. C, our B, likewise, then our C. So I have another 2 ohm, another 2 ohm. 2, 2, 2, right? And we've transformed the delta to star, so there is no need for the delta here. So I'm going to clean all the delta branches. So this branch should go nicely because we are done with that. It has been transformed. So take note. This branch will also go nicely. You don't need it. So let me draw that part well. So I actually wanted to clean this. This is not a branch. This is where the 6 ohm is, right? That is this part. So I'm tackling the resistors. So I'll clean the branches with the resistors, meaning this will go and everything here will go like this. Then this part will also go, tackling it this way nicely. If you do it carefully, you have a perfect drawing and you wouldn't encounter problems. So at this point, you can clearly see that I have a 2 ohm, 2 ohm, 2 ohm, a star connection replacing the delta, right? And it's nicely done here. At this point, we can proceed with our simplification. So see, these 2 ohm and these 3 ohm are clearly in series because there is no node between them. Hence, I'll combine them and it will become 2 plus 2, what is 5. So this will go and I'll clean and replace with only one resistor with magnitude 5 ohms. Now let's see. These 2 ohm and these 3 ohm, you can see there is no node and the same current will be passing through. So I'll replace the two of them with a single resistor and that will be 2 plus 3, 5. So I'll replace this and I'll replace that with just a single resistor here. So let me draw a single resistor here, 5 ohms. And at this point, you can clearly see that this 5 and this 5 are in parallel because there's a node here, there's a node here, and the two of them, upon retransversing through their path, you will not meet any other element. And their effective combination will be 5 by 5 over 5 plus 5, 25 over 10, giving us 2.5. Is that not it? So meaning I'll clean these two resistors and replace it with a single resistor of magnitude 2.5 ohm here. So I'll have 2.5 ohms here. Now you can clearly see that I have my 2 ohm, 2.5 ohm in series, and the two of them combines as 2 plus 2.5, which is equal to 4.5 ohms. So I'll clean that whole branch and replace it with a single resistor of magnitude 4.5 ohms. So let's see. So this becomes 4.5 ohms. This is where the problem arrives. I have this 3 ohm, I have this 4.5 ohm as the only two resistors which are within these two terminals. Are they in series or parallel? Please take note. From here to this terminal, this side becomes a node, because if current is flowing, you realize that there is a third branch meeting this branch. Here, also introduce another node here. So please, since there is a node between these two resistors, never think they are in series. We can redraw this circuit. Okay, so let me go back. I want to say that when you arrive at this junction, after simplification to this part, you realize that 3 ohm here and the 4.5 ohm are the only two resistors left. Never think that because there is no source, they are in series because you don't see any node. No. Whenever there is an introduction of a terminal, that is this A and this B, you realize that the terminal moves inside here and it's split into what? 3 ohm here and move up. Split here and move up. So you have something like this. And at this point, you can clearly see that there is a node here, this way, right? So let's see, though there is no branch here, but once this third one is meeting this, there is a form of T junction here. So this becomes a node. Likewise, this becomes what? A node. Hence, the presence of a node between two resistors doesn't make it series, right? But it can make it parallel. And now let's traverse through their parts. They are the only two resistors in this loop. We can conclude that 3 ohm and 4.5 ohm resistors are in parallel. Hence, our RT, total resistance, becomes 3 times 4.5 over 3 plus 4.5. You take your calculator, you punch this, and let's see. 3 times 4.5 over 3 plus 4.5. And that is giving us a value. So 3 times 4.5 over 3 plus 4.5. 4.5. Confused. Wow. Okay, so there is a comment that there is a confusion for this whole question, so I think I need to go over it again. So please pay attention as I speak over it once again. Pay close attention, please. So I'm going to take it step by step. I think I need to select this page. Okay, so I'm starting this question on a new page. So please pay attention as I solve this problem. I have a 6 ohm up here, a 6 ohm here, then another 6 ohm here. This comes down to a 3 ohm, this comes down to a 3 ohm, this comes down to a 3 ohm. This is to a terminal A, to a terminal B. Here is 3 ohm resistor. At this point, the problem is to find the effective, so calculate the effective resistance of the circuit. Please pay attention. This is what the question says. Calculate the effective resistance of this circuit, right? And you shouldn't be scared up by the arrangements. But what you do is you are going to take two resistors at a time and you work away from these terminals. Moving up, you can see that I have 6 ohm and this is ohm, which I can clearly tackle it. But the question is, are they in series or parallel? You can see that when you move, between these two resistors, there is a node here. Once there is a node, they can't be in series, but they can be parallel. But that doesn't mean they are. But what do? We traverse through their paths and see if these two are the only elements in the loop. But upon traversing, we realize that we encountered a third resistor here, 6 ohm. For that reason, this and this are not in parallel. So they are not in series. They are also not in what? Parallel. And that is where you remember the concept of what? Delta star transformation will come here. So meaning that 6 ohm, 6 ohm, 6 ohm are in delta arrangement. When we come down here to we realize that I have 6 ohm here and I have 3 ohm here. There is a node here, meaning they can be parallel, but they. So we can say that this is a delta arrangement. When I come here, 1, 2, 3 is also a delta arrangement. Now that we are going to apply delta to star transformation. Watch closely as I transform the delta here to star. So I have my 6 ohm. Let me redraw white. I have this side. I have this side. Then I have this side. 3 ohm, 3 ohm, 3 ohm. This is 6 ohm, 6 ohm, 6 ohm, right? Then this place move to the terminal A. This side move to the terminal B. I'm to convert the arrow shows a circle. Okay, so let's see. Now there is 6 ohm here, that is this side. Now I have this and this being in a delta arrangement, right? So once it's in delta, I have to convert it to star. And converting it to star, I told you that you introduce resistors between any two of them. So So I have this. So A, B, then C, right? To convert the delta to star, the star transformation has resistance or resistors A, B, and C. So let's see. I have my A. What's the magnitude? From our delta to star transformation, we made it known that if you have a resistor between any two resistors in a delta transformation, you just multiply the two resistors over the sum of the three other resistors, or the sum of the total resistors, that is the three resistors. So please see, A is between 6 ohm and 6 ohm. So to find the value, you get 6 by 6 over 6 plus 6 plus 6, where this is the sum of all the three resistors, and this is the product of the two resistors which A finds itself between. This gives 36 over 18 and giving me 2 ohms, right? I have B, that is this B, is between 6 and 6, so 6 by 6 over 6 plus 6 plus 6, and that is giving me 36 on 18, which is 2 ohm. C, 6 by 6 over 6 plus 6 plus 6, also 36 on 18, which is 2 ohms. At this point, we found the values of the resistors on the star transformation. For you to understand clearly, I don't want us to redraw it on the next page, so please watch. I'll be cleaning this part of the circuit for you to see how it is being transformed. My ABC will go and I'll replace them with their respective values, and you know their values are equal, which is what, 2 ohms. So this is 2 ohms, 2 ohms, then this is also 2 ohms. The next thing is the delta resistance will vanish because we've transformed it. So 6 ohm here will go alongside with its branch nicely. Then this will also go like this. This resistor here, 6, also go. Then you can see that it's also going. Now this is the shape we are left with. So with this shape, we can proceed. Once we remove these branches, this place becomes a single branch. So 2 and 3 ohm here becomes in series. So their effective value is what, 2 plus 3, and that is 5. So I replace this whole branch with a single resistor of value 5 ohm. And that is exactly what we did. So here is 5 ohm. Now I have another combination here. This place are also in series because there is no node between them. So please see 2 plus 3 will also be 5. So I'll clean these two. Then I'll make here 5. Right. So let me clean the whole branch and do it straight. So I'll have this, and this becomes 5 ohms. So 5 ohm, 5 ohm, we are working away from these terminals. So realize that these two are in what? Parallel. There is a node here. When you move around them, they are the only two resistors. So 5 times 5 over 5 plus 5, and giving us 25 on 10. So this 2 gives us 2.5 ohms. Meaning I have to replace the 2 with just a single branch with a single resistor of resistance 2.5 ohms. So watch as I remove this whole branch and replacing it with this, and this place now becomes what, 2.5 ohms. Is that not it? So now we can see that our circuit has been simplified, and this place is a single branch, so the same current will be flowing through them. Hence 2 ohm and 2.5 ohms resistors are in series. So I replace the two with their effective combination 2 plus 2.5, and that is 4.5 ohms. So I'll have this leaving, and this will also leave, and their combination was 4.5. So this becomes a straight branch. So this is just a straight branch, and their combination here is what, 4.5 ohm. So this is where I stopped and I was explaining that 3 ohm and the 4.5 ohm, never think they are in series, like the same current to flow through them. No, please. The reason is there is a source here coming, and this here becomes a node. This also coming from the source, this here becomes a node. So please, this connection here, because of the presence of these two nodes, make it parallel, right? So once they are parallel, if you really want to see this well, we can redraw it this way. You can see that these parts are not necessary, so you just clean this side. Yes, then make it so simplified so that you see clearly that they are in parallel. Yes, so now you can see that they are in parallel because there is a node this way. Hence our RT is equal to 3 by 4.5 all over 3 plus 4.5. And at this point, you take your calculator, you enter the calculator, you enter into the calculator the expression 3 times 4.5 over 3 plus 4.5. And this is giving us our RT is simply 1.8 ohms. And that gives us the effective resistance of this whole circuit. And this brings us to the end of delta star transformation. And there is an assignment which we are going to solve on this page. There's a problem which we'll be solving. So that will be for the next page. Can we send it assignment so that I'll be able to present? Yeah, that's true. Okay, so there is a question here and it says find the value of the current in all resistors of the circuit below using total resistance and voltage drop principles. Do not use current division rule. So let's see the circuit. We have so let me draw this wall. This way. This. So I have this place to be 2 ohms. This part is 25 volts. This is 1 ohm. This is 4 ohm. This place is 3.5 ohm. This is 3 ohm. This part is 5 ohm. Then I have 7 ohms. So the problem is find the value of the current in all the resistors. Here, 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 here. But you shouldn't use current division rule. Instead, you have to use total resistance. So here, total resistance and voltage drop principles. Please watch closely as I take you through this and listen attentively. So, as the question says, we shouldn't use current division rule, but instead total resistance. The first thing is to find our effective circuit as well as the effective resistance. What's the effective circuit? To find the effective circuit in our previous examples, I told you that you are to trace the path of the current if you are given any circuit with a source. I have a 25 voltage source here, 25 volt source, and it will produce a current I. This current I here will pass through the 1 ohm because it has no other option. It's the only way. And upon reaching here, you realize that this current was split. Some will pass through this side, that is the 2 ohm, and some too will continue the journey. The rest will continue, and upon reaching this junction, we'll have another decision to make. Part will pass here, then the part will pass here. It will reach here, this part will reach here, and upon reaching here, it's going to make a decision. Should I move down here? Should I move here, or should I move here? There is an obstacle here down here, then there is another obstacle here. But I can see a free path which I can pass through without any hindrance. Why don't I pass that and skip these two obstacles? That is what we call short circuit, and we talked about it earlier. So our current I will simply pass through this and pass through here I and return back to the source as I. Hence, it is going to skip this and skip this, meaning that 5 ohm and 7 ohm resistors have been short-circuited. Short-circuited. Take note. And this tells us that we need to draw the effective circuit. To draw the effective circuit, we need to omit all the resistors which have been short-circuited. So please watch closely. I'll have this resistor here, this one here, then I'll have this one here, this, then the short circuit will come directly back. So here becomes 2 ohm, here becomes 25 volts. Here is our 1 ohm, 4 ohms. This place was 3.5 ohms. This is 3 ohm, then like that. So let's compare 3.5 like that. Yes, you are right. So this is the effective circuit, and once you have the effective circuit, we move on to the agenda, and the agenda is to find current I in each of the resistors seen in this circuit here. To find I, you always know that from Ohm's law, V is equal to IR. To find I need to get my total voltage VT over what? Total resistance RT. To find I in each of the resistors, you have to find the voltage in that particular resistor VR over the resistor itself, that is over its resistance. This is what you are going to use. Please take note. So we need the voltage across that particular resistor as well as its resistance to get a current through it. So let's see. Current I, as I said, will start from this side. Now that we have the effective circuit, we can go ahead to find the effective resistance. So watch closely. 3.5 ohm and 3 ohm is a clear series connection because there is no node here. For that reason, these two parts becomes 3.5 plus 3 ohm, and that will give us 6 ohm. So let's see. I want to take my time and redraw this for you to understand this part. So 25 volts, 1 ohm. This is 4 ohms. Then you realize this part becomes what? 6.5 ohms. Let's see. Once you have this 6.5, you can clearly see that this and this are in parallel because there is a node here, there is a node here. When you traverse through their path, they are the two resistors you are meeting. So they are in parallel. And their parallel connection is 6.5 by 4 over 6.5 plus 4. And that is giving us what? 6.5 times 4 over 6.5 plus 4. That is giving us 52 on 51. on 21. So 52 on 21. And I told you never leave your answer in decimals until you are done. So I'll redraw the circuit and I'll be getting something this way, my 1 and my source back. So this place becomes the 52 on 21 ohms. Here is 1 ohm, 25 volts. This place is 2 ohms. 2 ohms. So now that you have this, working away from the source, we tackle 2 ohm and this, and they are in parallel because there's a node here, there's a node here. When I traverse through their paths, I'm not missing any other element. So 2 times 52 on 21 over 2 plus 52 on 21. What am I getting? So 2 times 52 on 21 over 2 plus 52 on 21. And that is giving me 52 over 47 ohms. Now I'm to clean this and replace it with a single branch. So I'll have my 1 ohm, this ohm, then my source 25 volts here. So 25 volts, 1 ohm. Then this place will be what? 52 over 47 ohms. And now you can clearly see that it is in series. So my total RT is equal to 1 plus 52 on 47. And that is giving me what? 1 plus 52 on 47. And that is giving me 99 on 47 ohms. This is the total resistance. Now we need the total current I here as we started. So IT is simply equal to the total voltage 25 divided by 99 over 47, which is the resistance. So what are we getting? 25 over 99 on 47. That is giving us a huge number, and we are getting 11.87 amperes. So this is the total current, 11.87. I left this in decimal because it's my final answer. If not, I would have left it in the fraction until I finish. So once I have 11.87, that will be the current from this side. So now let's come back and come to the agenda. We have to find the current in each, not the entire current. So first of all, the same current which is coming from the source will pass through the current in 1 ohm. So let's see our answers here. You realize that the current I of 1 ohm, please, that's the current in 1 ohm, is equal to the total current 11.87 amps. And that is the first part. Once the current passes through this, a voltage will be dropped here because there is a resistance. So what's the voltage dropped across this 1 ohm? You know that the voltage drop here, let me clean this side. As the question said, we should use voltage drop as well as total resistance and not current division rule. So I want to illustrate a voltage drop here. So once the current passes through this 1 ohm, a voltage across V 1 ohm is equal to 1 itself, that is the resistance, times the total current passing through, 11.87. Hence, I'll get 11.87 volts, which is deposited across this 1 ohm. So the 25 volts here will have part of it deposited here, and the rest will then be distributed to the others. So once I know that 11.87 volts out of this is deposited here, the remaining voltage becomes 25 minus 11.87, and that is giving me what? 25 minus 11.87. That is 13.13 volts. So once you have 13.13 volts, that is the voltage across the others. Now, you know from your basic electricity principles that if a resistor or if an element or a load is in parallel with a voltage source, then the same voltage will be across that particular element. Hence, the voltage across these 2 ohm is what? 13.13. Take notes because it's in parallel, so that's the voltage across it. So to find my I, 2 ohms will be equal to what? My voltage 13.13 over its resistance 2. And that's going to give me 13.13 over 2. That is 6.56. So let me leave it to 2. I'm going to get 6.57 amperes. And that is I 2 ohm. That is current across 2 ohm. Now let's come back to, so I'm done with this. I'm left with these parts. So as I said, any resistance or any connection which is in parallel with a voltage source has the same voltage as the source. You can clearly see that this 4 ohm here is also parallel towards this side. So the voltage left 13.13 will be the same voltage across this side. So if you really want to understand it well, when we were simplifying this circuit, we arrived at this point. We combined this to get this. We combined these parts and we got this. So you can clearly see that this is in parallel, this is in parallel. So the voltage across the 2 ohm is the same voltage across the 52 out of 21. And 52 out of 21 here is the same as the combination of what? 4 ohm and a 6.5 ohms, right? So let's see. Now the voltage across this side is equal to 13.13. Is that not it? So that's the voltage across this connection. So please take note. This 52 over 21 here represents this combination. So meaning that the voltage across this whole side is equal to what? 13.13. So you can clearly see that this is parallel and this whole side is also parallel. So now the voltage across this whole thing is 13.13. Now let's see the voltage across this alone. If you have any two resistors in parallel and the voltage, you have the voltage across them. So see, this side is in parallel with this. Is that not it? Because there's there's a node here, then there's a node here. For that reason, the current that will be passing through this, to find, if you get that and you multiply it by this, you are going to get the voltage. But now we have the voltage and you have to find the current. So realize that these two which are in parallel will have the same voltage across them. So the voltage across the 4 ohm here will be 13.13. So to find the current, I 4 ohm will be equal to, so I 4 ohm will simply be equal to my 13.13. So let me clean this. Is going to be equal to 13.13 over 4. So 13.13 over 4, and that is equal to 3.28. So I have 3.28 amps or ampere. The next thing is to find the current across these two, 3.5 ohm and 3 ohm, but they are in series. And you realize that the voltage across this is the same as the voltage across this side. So the entire voltage across this 6.5 is what? 13.13. But the 6.5 has two components which are in series. So voltage division sets in. So at this point, you realize that the total voltage across this 6.5 is what? Is 13.13. But I need the current through each here. To find the current, you need to use the combined resistance in this branch. So therefore, let me clean this side so you understand it well. So you know that this 13.13 is the residual voltage across this whole section. So across this and across this, because they are in parallel and they are equal. So meaning across 4, we got its current. So across this whole thing, if you know the voltage across this whole branch, to find the current, you need the total resistance across that branch as well. So we're going to use this. So you have I to be equal to V over the RT, where V here is the total voltage 13.13 across the two, and their total resistance is 6.5. Is that not it? So you have 13.13 over 6.5, and that is going to give us 2.02. So I'll have the current across this branch to be 2.02 ampere. But take note, if two resistors are in series, then it means that the same currents are flowing through the two of them. So my I 3.5 ohm is equal to 2.02 amperes, as well as my I 3 ohm is also 2.02 amperes, since they are connected in series. So at the long run, you can see that we have a list of the currents across each resistor, and we use voltage division as well as the total resistance, but we didn't make use of, so we use voltage drop as well as the total resistance, but we didn't make use of current division. So this is the end of the tutorial section, that is for applied electricity. Thanks for being with us through and your patience, and hope seeing you next time on the same platform. Please kindly fill the form and give us the feedback of this tutorial section. Is it recommendable, or we should, give us suggestion or anything? We just need the feedback to see how you're going to go by the tutorial section.